Thank you very much. Yeah, first of all, I'd like to thank organizing the invitation. It's really a great honor and have a chance to speak a great scientist thing here, and certainly very challenging for me. Can expect talk about be very mathematical, and but I'm looking forward challenge whatever questions you're raising from audience. So instead of working on specific question, I was very impressed by yesterday, all the talks. It's amazingly learned a lot. I have to digest all details. But so we tend to be speaking more general, so less specific. So I will take excuse. And okay, so this sequence work, which I have been working with last few years with people. And so basically say, in classical, chemical reaction, non-equilibrium reaction, and would like to see if any kind of mathematical structure we can bring to the system, which we, at least mathematicians, can understand. And hopefully, there's some thinking what we bring to will be useful in some sense application. That would be very appreciated. Okay, so now here sort of basically you look at the system. It's a classical, not quantum multibody, just work classical chemical reaction. But I would like to see microscopically what's the structure in the equation. Basically, I want to say bring to the Hamiltonian mechanics into this system so that we can do understanding. So that's the sort of purpose along this line. Okay, so let me just beginning with sort of the structure. I want to bring to what kind of things we can bring to. So first look at the general chemical reaction. Think about a stochastic process, a jumping process, the usual. And then look at the equation itself. What is the dynamic in the limit of thermodynamic limit? You take the larger volume and the minimal chemical potential, special homogeneous, and I'm not doing reaction diffusion type. So then you can study larger deviation, and then you studying what's the limit equation, you satisfy the Jacobi equation. Hamiltonian is coming now first. So now what is this Hamiltonian will help you to understand what is chemical reaction, and particularly like reaction equation, which is system equation, complicated polynomial, and is there any Hamiltonian structure in there to help you? So that's the sort of question which are studying. And first of all, make sure what we said is reasonable, and that means all the studies here, large deviation, semi-group, as rigorous. At least we mathematicians have to bring say something is backup is we can do rigorous proof. And it's what said is precisely accurate. Condition is different question. So then what we really say, so with this understanding, then how much we can say about chemical reaction? I would say, and first of all, write down chemical reaction in terms sort of the Hamiltonian structure. Okay, Hamiltonian structure, two equations. First equation, and this is one part of the equation. And why? Because good reason I'm going to explain from point of view of larger deviation. You see clearly this is true for because this chemical reaction is the law of larger number. You can see have the structure. So then you can bring to decompose the chemical reaction system itself in terms of conservative Hamiltonian system plus dispersive system. And they can say why they reach equilibrium, how to reach the equilibrium. So sort of the energy landscape, and you hovering around the local minima, how to hovering out. So that's a question I'm going to explain. And I explain so energy landscape. Now chemical reaction itself is not it's not detail balanced. And where's the energy landscape? How it come from? Everything come from larger deviation. You can study. And then this energy landscape itself, to help you, you actually can use it to do sort of whatever would be in the analysis. So that's sort of, and finally, of course, in applications of called computer transition path. So that's classical transition path theorem. But what's the most efficient if it's solving? And it bring like sort of optimal control theorem to make this speed up, because the Liu event can bring to this one, make it the almost surely event, make it extremely computer fast. So that's sort of idea, and I call it the important sampling. Basically, it's the idea of really important sampling. So that's sort of my plan, and not guaranteed to explain all. Okay, so let me just, first of all, let's make a notation agree upon. So general chemical reaction. So a group of the molecules over there, left and to right. and you have the forward reaction, backward reaction. And then reaction itself, we just saw, okay, so I have to say a little bit details because I want to make a rigorously stochastic analysis. So you do one reaction, you have Poisson clock, your reaction, you change the counting. That's all we have, right? Just reaction happens, then, from source to the target, back and forth rate. And the rate itself is, okay, but here is like a molecular species, like fixed n size and container. Species have here, and so the forward, backward reaction vector itself, and this plus means forward minus backward. And that's me just, you look at the coefficients, for example, 2 or 1 or something. So that's the vector counting the group of this molecular species on this one and to right, so you can change. Notation. I just, okay, before I have to say notation, otherwise calculations, everything is elementary. Okay, high school math, the chemistry. Okay, so now, okay, so what we all know, so the things, law of mass action, how the rate encounter, how the fast it is, and then you over there, and this is the equation, wrote down 100, probably 50, 60 years ago. Okay, reaction equation. As we normally do classically, is the reaction is to this equation. So that is the vector equation, no structure. Although there's some structure, polynomial, but a complicated polynomial. And where the local equilibrium is sort of where the station is there, then you are able to change it. So this looks simple, but it's not actually that simple. We all know sort of how to hovering around local minimize, because that's what exactly I want to bring some sort of Hamiltonian structure to understanding. Okay, so let me, before doing this complicated things, let me use the most simple mind ideas to see what we are thinking. Then I can bring to rigorously to the general case. So let's most simple mind. Okay, it's complete mind. Okay, you make it complete simple. So you have suppose you look at the system itself with meaningful if energy landscape potential. Okay, so and of course where the potential come from. So that's what I'm going to explain. So now suppose the potential, and then you have the stochastic process. Let's do in Brownian motion, just simple as possible. Think about it. You have Brownian motion. So then you want to say computer. So if I have the source here, I have product here. I have to overcome this energy landscape and jumping along, and I have sort of the chemical reaction happens. So that's what we care about. They call it transition path. And then you want to compute the most likely happens. They call it most probable path or transition path. You want to compute this one. Now, okay, so this idea is developed in 30s, right? Let's call it transition path theorem. Okay, but what do we need to do with bring to the, okay, now first of all, I want to bring Hamiltonian structure here. So where I come from, then also when studying instead of the Brownian motion, I start really jumping process. Then I see you probably want to say, you bring some of, once you have structure, you can study this question. So now this is a real event. It would be, of course, noising to hovering and make it a cup, but what is other way to do it? As called, yes, go ahead.
May I ask a question?
Yeah, please.
In your system, the capital X are just the reacting species.
Yeah, yes, yeah.
When as a solid state physicist, I could also take all the coordinates of the atoms, and then they would be in your equation. That's where the Lagrange equation applies.
Yeah. Now, solid state physical crystal lattice is a little bit slightly different, because then over there itself, because the nuclear stays there and the electron hovering around. So this is what I talk about is more like the chemical. It's because at least the crystal the structure is special variation we have here. Here's no special things because everything contains reaction. So okay, now solid state. Okay, this is not quite really applied to solid state. Okay, yeah, okay, but good, yeah, sorry, thanks for the great question. So anything is how we can bring to something. So now first of all, so what we need to do with this guy, it's not a simple question really. So what is really is that you compute the most of the likelihood path, but exactly not to change the original problem. If you want to change the original problem, easy, I just bring this guy to there, it's easy to do. Anything you want to follow exactly path, you cannot change this path, bridge I call it, one. And then you want to say most likely have easiest way to do that is in this guy called Fernando-Wenzel theorem. you do large deviation problem. When you bring the sort of vector convection, then you do the computer the commute function and solve it, and you guess the computer is very efficiently, most likely. But now this is not chemical reaction. And how this idea more generally used for chemical reactions, that's something I want to bring to here. But this was starting point. So Friend-Wenzel theory in large deviation is used a lot in the chemical engineer, but I want to bring to the math. Okay, so I had to say something a little bit of details, explanation. So first of all, what is the process? You have container. In many species, molecular species there, you do reaction, you Poisson clock, you do reaction here, and of course, everybody in chemistry call Gillespie algorithm. That's exactly algorithm, also process. But this process itself very easy to computation, but less easy for the proof, for the derivation. So that's equivalent. So that's the Gillespie algorithm in chemical reaction, and this algorithm is probably most friendly way called the London time change Poisson process by Tom Kurtz in 80. And this equivalent to all the processes probably depending which background. Marx, Nonequilibrium and Gillespie's identical then. Anything with different implementation, different realization for stochastic process, but it's used friendly. And this sort of why friendly, okay, it's very nice. Only one thing involved called RID, independent identical Poisson rate function. So that is very easy to have here. Poisson clock, you just everybody can do correction. Then you slightly change here is the rate because history was involved. So because the particular species itself has different time and different so you have to do an integration. And this was called the London time change. It's because everybody clock have its own clock to counting how much. Okay, sorry. Okay, I get spit out. Okay, so then you can. So that's a reaction equation you have here. That's describe container. I doing something with volume V, 1 over H. I change it easy for me. I use 1 over H. So basically, you see the question is called thermodynamic limit. I mean, large volume, large species, what's the limit will be? So that's called a large deviation question. Okay, so okay. So I'm doing some of quick comparison. So that's something everybody familiar with, just drop diffusion, everybody knows. But this correspondence sort of chemical reaction, slightly complicated. At least I can bring to you sort of for the Hamiltonian structure, say, at least for reaction part you can easily see, but then Hamiltonian part is really interesting, I want to bring to, okay? So now you write down this stochastic process, you write down this Fokker-Planck equation, so you make a slightly change variables. So that's where variables, let's say, by the way, so this idea not directly come from a mathematician. It's actually idea come from the, I guess, who the, probably the physicist would be first come up with this called ideas to do that. Okay, I think what is doing the, okay, getting older. Okay, to make a simple change, WKB kind of ansatz. You plug in here, you write down this reaction equation, we call it cohort transformation, whatever. Okay, so you write down the Hamiltonian structure and have epsilon, and this guy could be 0, is exactly, you see the Hamiltonian system. At least see where the Hamiltonian come from. Okay, so that is for diffusion, but at the same time, you work on chemical reaction for jumping process, you can do identical similar things. I don't bother you with details, but okay, it's structure. And you can study in the sky, and now you have the structure. At least I bring to the Hamiltonian structure here, and you will see what's useful for the Hamiltonian structure. Okay, so that's one. Okay, so let's see. So everything is rigorous. As a theorem called the large division, they called Vardin's lemma. So what does here is called a nonlinear semigroup. Okay, semigroup means just okay. No memory. Okay, Markovian property. So you're doing this kind of things here. The beautiful theorem, okay, the Vardin says this guy, for nonlinear semigroup itself, if limit itself converge into limit of another equation, which is a sort of viscous solution to Jacobi equation called a Hopf flux formula. Okay, you're doing all Lux or link, depending on which content you talk about. So this is mathematics to large division prove this converges rigorously to prove this guy. In other words, so this kind of these are identical system to chemical reaction. Look at the law of the distribution of chemical reaction. Write down the very friendly way to find the difference. but upwinding skin. You have a structure over there. And once you write down this very nice structure itself, you take a limit itself, you guaranteed this limit itself, you get a solution to the Hamiltonian equation. Complicated, okay, but at least structure-wise is clear. So I will not bother you details proof, but I just give outline the thinking. So, but only thing the important I want to say is so at least you're comfortable with this maximum principle, whatever property you can maintain, you have a good property. Let's go on. Okay, so you just this is a Liggins theorem and the large deviation. Important here question is the limit itself. You have the large deviation property. Okay, now so I continue jumping all the math stuff. Okay, so first things here. So you have the jump as a rate of equation based on some energy, the one. So for this guy itself, you can give the rigorous proof with sort of the helping from numerical analysis. You can rigorous proof the large deviation, very complex things. At the same time, I had to say the Danbo from Stanford is actually, they also have a stochastic way to prove earlier than us, but it's rather complicated. Other assumption, I'm not quite sure is verifiable. But what we have here is complete elementary. Okay, you just doing the whatever something you can prove the large deviation theory. Okay, now, what's the here of large deviation? What has the useful to the chemical reaction, right? So I'll tell you it's relevant. So let me bring to the results. So let's give you some. First of all, let me tell you, large deviation do bring to us some of good Hamiltonian structure to chemical reaction. First of all, this Hamiltonian itself, the Hamiltonian means that duality have Lagrangian Hamiltonian from classical mechanical way. And this Hamiltonian Lagrange itself have very special property, which means non-negative. So it's just directly verified considered non-negative. So now this gives you important property. So what means law of large amount? Most likely happens as called a chemical reaction equation. Would we everybody work on this guy? So now this I bring to this guy itself. So this guy is a chemical reaction equal to 0 if only if it is a chemical reaction or law of large number realized. So that means you can actually, this everything can easily verify, prove this guy. So this is our chemical reaction. It's not on the solid state. Okay, it's really, one and classical. You have the complicated polynomial vector monster over here. Now I bring to the structure. So this is actually nothing but Hamiltonian with particular choose p equal to 0. Why p equal to 0? Because it is the law of larger number. Its momentum is 0 because its Lagrange is 0. So that is the first thing here. And this large deviation is also given to you prove indeed the Meafield limit. So it's chemical reaction, the limit equation, then you have the concentration estimate. And first, of course, proved by Tom Kurtz in 70s with the one, but now we have bring more than the you should have here. You have the rate, precise rate he computed here for this mean field limit concentration estimate. Okay, so now I want to bring number of the interesting phenomena to along this understanding. Okay, first of all, Hamiltonian structure can naturally come in because the large deviation, the Lagrange is non-negative. And the law of large number exactly is Lagrange equal to 0, London cost 0, and bring to this Meafield limit. Now, suddenly we have structure for reaction. Okay, so it's Onsager's thinking. So you basically, any chemical reaction itself, we can write down Hamiltonian part and plus the green floor, which is cared about yesterday, so now, but you need, first of all, determine the energy landscape. So I'll now bring to the energy landscape. That means solve this Hamiltonian steady state solution. And this turns out to be very tricky. I'm going to explain afterwards. So suppose now you trust there is energy landscape describe the chemical reaction, which is a stationary solution to this Hamiltonian. Okay, first take it, then I explain where I come from, how to study. Okay, so given this energy landscape, assuming it exists, okay, because it exists is a complicated issue, it's a very complicated issue. Okay, so you now write down this very nice reaction equation, complicated polynomial nonlinear reaction system. Now we have, okay, it's very simple. Indeed, the Hamiltonian structure over here. So now I can decompose two parts. So learn from Onsager. Onsager says doing some slightly different complications. You're doing okay, mass trick, okay? It's useful for mass trick. It introduces this energy landscape. You Hamiltonian. You're doing sort of kind of the average as K called the Onsager response function. Okay, so now then also W analysis average over there. Then actually chemical reaction in terms of Hamiltonian part plus dissipation part. Okay, so why? Okay, at least I can explain. First of all, this guy is average is 0, nothing change. On the dynamic of chemical reaction, Hamiltonian is sort of keep a constant Hamiltonian, not change. But then Gaudian part will give you the will leading to the equilibrium you have here. So that's the one I have here. And because you can say anything, what's the Lyapunov function of free energy have? So energy landscape itself exactly the Lyapunov functional. You on the chemical time change, you plug in here. Let's go. This is how much dissipation you have here. It's exactly a picture for Onsager cells. Actually, when I read this paper, I read the original paper Onsager, 1931, and sort of the simple example, actually exactly the Onsager thinking. He actually used this function. Okay, so you K here, you come up the dissipation, you have this guy. And if with some kind of symmetric case, some chemical data balance, whatever, and then you have very simple, just simply Gaudian flow. You have here. Okay, first of all, now bring the structure to this whatever, at least for math people comfortable with, we can work with this. The first question. Second question is connection between stochastic process and limit equation. You bring Hamiltonian structure and you back to the original question, how this Hamiltonian structure was originally be. Okay, so this part is not completely rigorous. It's much harder. Questions, but there's things you can say here. At least structure-wise, you see something correspondence. So, of course, I begin with pi, means equilibrium invariant measure for the jumping process. Okay, because this one is a highly non-trivial question. Let's take it as ground. Okay, so now you take this guy itself. You take a minus log divided by volume V. Take a limit itself. First of all, heuristically. These are given to you energy landscape. And this is solution to the stationary Hamilton-Jacobi equation you have here. So now then, anything whatever we think about the natural way, so you look at the stochastic process, jumping process, look at the sort of relative entropy or Kerr divergence, and you see certain dissipation property you have here. And this guy, you take a limit is identical to structure what I explained on this Hamiltonian structure. So at least you see this structure was there. From microscopic passenger to the microscopic is a passage over there. You see the quantity here. And then, of course, even looking more carefully, what is adiabatic, what non-adiabatic contributions. You can do detailed thermodynamic analysis. We actually in the paper we give very detailed study in this question. Okay, so but it's so this passage from microscopic to the mesoscopic is there. So that's you can do correspondence depending on how you're comfortable with this guy. Okay, so that's a structure we bring to. So now then, okay, so now I want to bring practically what is the energy landscape come from. Okay, so this sort of the question from dynamic system called VKKM. I'm going to explain a little bit. Okay, so first of all, I bring to the, okay, first of all, this is very complicated. So complicated, so this picture is very dynamic picture. So you want to compute this guy, basically starting from X, where to go to attract, how much cost you have here, you're doing this guy, infimum time go to infinity, that's called, okay, so the time horizon go to infinity, you have here limit is that. And then you suppose, so any for this guy's solution to this stationary solution. So many solutions, not unique. Anything, what is the right equation you pick up? So that's the tricky part. That's called the VKKM, or the large deviation. Okay, let me explain. Okay, so basically, at least say there's many energy landscape, but none of these are relevant. Only one relevant, which I'm going to explain. Okay, so one, so that's his, okay. Here's a small story. I use simple example to explain. So in the weak Km, in the PD sealing is fashionable after Pierre Lyons, and the many people recently. The basically question that is a stationary solution to Ham-Jacobi question not unique. How to select a solution which meaningful, and the viscous selection is not enough. So that's come up called a large weak Km selection. So that is theorem. But now I was reading a book by Frank Wenzel. I always look at for chapter 1 to 7, never look it up after chapter 7. So then suddenly I look at chapter 8. Suddenly to my eye, open eye, this formula pump up in the Frank Wenzel's book. It's did 1969, far away before the Pierre Lyons was did on this weekend, all the theorem. And it would be both of them extremely smart. Actually, Mark Flannery was my colleague at University of Maryland. Okay, so they have really theorem for weak Km theorem, and this way before this the mother theorem in dynamic system. Okay, now here's sort of a nice trivial question. So let me explain. So what is energy landscape means? So we have many how to pick a right one. So he's studying this guy. So this is the beginning. So let's say my picture is this guy. I made example which from the book. You have the very simple energy landscape. It's local minima, and this this is not original, really not the energy landscape. So what he does here, you have to do some large division here, large division here. So now you're studying the balance. You have to lift up. You balance for this equation satisfied by called a discrete with Km. Then you determine actually the chemical reaction energy is this one, suppose the correct solution to the energy landscape. You sort of need the balance between the local minima. So that's to say how much this chemical reaction stay on the local minima, how much time really stay. So that's sort of theorem was when as Corby came. At least I tell you, energy landscape is not a simple question. Okay, so that is one. Okay, so now let me to bring to this one. So this picture I showed before. How practically how we do computational, how we compute the transition paths in an effective way. So let me bring to remind you what we do. Of course, these are most people in chemical engineering. It's obviously okay, Frank Wenzel. We do this way, but these are big assumption. Like assumption here, you say reaction question, you write down this detailed balance form or gradient form, but actually not. Right? That's what you have to be complicated studying this energy landscape Hamiltonian structure. You bring to this guy, and then of course you have the Brownian motion. Simple as possible to think about stochastic process, but actually jumping process. It's not identical, same thing. And then practically actually is different. So I want to first bring to the idea Frank Wenzel, then to actually chemical reaction, do the calculations. Okay, so I have to really explain. So there's the good way to think about. Okay, so first of all, the Frank Wenzel theorem, or large deviation is important here. You say it's going to change the system or important sampling. It may change the counting for probability. So that means I look at the system, original system, let's bring V there. Control draft, the additional draft over there. And the draft is there, kind of minimize some least action, some kind of things. Okay, so now with this the new system itself, you compute the one, and this is friendly. Okay, and I do not have the word I said before. So this guy itself, then you Monte Carlo simulation yourself with additional draft. You bring to this A to B. You bring to this one. Then you no longer real event. Otherwise, beginning to calculate your long Monte Carlo simulation, 1 out of a billion or successful, most just okay, go back, right? So now you want to say bring out to the comfort zone, bring out to the attractor to the other place. You have to some mechanism to bring out, but you bring out it should not destroy original system. If we destroy original system, because very I just put this particle outside for the local attractor, you compute, but you compute nonsense. So you be careful with how to compute this guy. Is require really careful thinking. You need to bring out from the local, not put noise in, just bring out. It's not that way. So you need to bring out this particle from the local and minimize it into the way another attractor, which is a product you care about, And so that's sort of a way to that. So the basically says it should be not to change the most likelihood path. And then you want to bring to alternate shear events. So this is a paper with a group of people a few years ago we load. And we computation actually compute not like great, 40 molecules. So it's not a great idea, but we did do computation with math quite efficiently. So now I want to bring to linear chemical reactions. So this cartoon, cartoon we can work very nicely. Now bring to the linear chemical reaction complicated. So it's so complicated, and so that's something I want to explain the transition path theory, how to compute it, and particularly how to do the important sampling. Okay. So the question that, for jumping process, stochastic process itself, so there's many local attractor, but the attractor itself is not easily to distinguish. It's not like the draft diffusion, this draft the diffusion. For any chemical reactions for jumping process, just change the probability jumping rate. There's no distinction between what means draft, what means diffusion, nothing over there. So the only thing, what's the right notion for the control is the first important question. You cannot only put a V here over there. You basically want to alternate the rate of change. And then you alternate change yourself. You only think everything important here, computational friendly. You derive a theory which is realized computational. So that's something I want to bring to the question. Okay, so some of analysis is a lot complicated. I don't want to bother you with detail, but I want to give you the outline, the ideas. Okay, so idea itself is actually beginning come from the chemist. So the chemist is extremely smart, I have to admit. So look at that paper, is amazing. So this is called, first of all, let me bring to this called a commit function. So basically says this guy, I first introduce a very simple penalization. So you suppose if from A you want to go to B, you give it some force, infinity force. If you back to A, I penalize giving infinity, you will minimize something, it's never realized. Then this guy, if we go to B, you reward. That's a very natural rewarding function over here. And you doing here yourself with tau is called stopping time. First time the process reaches either A or B. And then with this guy itself a sort of additional force to bring to the system so that you always make surely, almost surely from A to B. And that's what we like to compute, called transition path. Okay, all right. So you're doing this guy itself. And so the one, so now, first of all, infinity is very singular. And anything infinity we call the mathematics called singular. And is a monster we have hard to deal with. Okay, and then probably this question we always keep in mind, you do something not to change the original problem. You compute a linear transition path. So that's something be careful. And then, of course, mathematically, you have to formulate a question called the martingale problem. In stochastic process, okay, you can do it, okay. We have a number of tools in our pocket that can solve the problem. Okay, so let me just bring to the first question, in formulation question in terms language of important sampling. So what the important sampling means? You have sampling some complicated energy landscape, and the variance is huge. As original, this energy landscape itself is an original probability distribution, which we chemical reaction have here. And what it does here is a very simple idea in the important sampling. I look at a different probability. I make up a different probability space so that in this new probability space or different weight in the important sampling, so that this energy landscape very friendly, very smooth out nicely, have the lower variance. So that's the important sampling means. Same idea, what are we doing here for stochastic process? So that means we call optimal change measure. So optimal control become optimal change measure. So just a different way to look at this process. I look at different the probability space, but this probability space has to be complicated in the path space. You have to do this later path space. You're doing the optimally change the path space so that these are friendly. So we basically viewpoint, but that's what friendly means sense Monte Carlo simulation most efficiently and nice and almost when see this game almost painless. I can see, but okay. Afterwards, I have to say we bring all the complicated tools solve the problem. Eventually back, okay, chemist knows. So that's something bottom line. That's what we always have to learn from chemists. So that's I'm going to bring to questions. But how to use it is still different from what we our understanding. Okay, so that's the first of all question itself. Okay, so now you look at this guy. Looks complicated. So here's omega is all the paths, like all the paths. Right continue, left continues the left elliptic, all the jumping process space here. So now this is a monster. Okay, looks friendly, simple, it's complicated. Okay, you're looking for optimal Q. You optimize this guy so that this is called optimal change measure, so that my relative entropy in the path space minimizes. So it's a good notion. Anything you surprisingly cross board from machine learning, chemistry, anything. Always use one simple ideas. It's why, and I'm going to explain this called relative entropy or Kerr divergence. It's almost universally appears different subjects except always the same thing. And that's what in calculation I show you what is why we do that. Okay, so in the proof next line I'm going to show you. Okay, so here's the line I had to explain to you a little bit why I was after working this one. I really appreciate how this general concept appears everywhere. Why? In machine learning, you people do chemical reaction, do the physics, always the same ideas, relative entropy or Kerr divergence. Okay, here's a property. I called this guy called the disintegration. A little complicated. Think about okay, change the variable formula in Fubini. Okay, so now there's one property, only one entropy function works beautifully called additive property. So that's I explain to you the proof over. So you first doing sort of kind of okay, it's just different way to compute. So disintegration is different way to condition something, and I do get different counting. So you write down this my okay. So some of we are change measurement, change Ardon decompose. Some of change variable formula Jacobi or whatever something in simple language called Ardon derivative. You write down this form. This formula, beautiful formula, universally appears. As particularly in machine learning, people use it all the time, so that's okay. So if we do this disintegration, you look at relative entropy, you have this additive property. You have this guy and this guy. Both are positive. If we minimize these things, you minimize each of that. Now, you minimize this guy, if we just set 0, it's always minimal. And if you set this 0 means you will not change a bridge between the process. So you not, first of all, you realize this optimization in an easy way. Secondly, objective, not to change any kind of physics inside. In that change, it's basically I do nothing. In the process from A to B, I change a different probability in the reaches A and B, but in the middle, I do nothing. So that's important. That's what keep my bridge are same. Okay. And then, okay, doing this. So that is the idea of proof. Okay, so, but it turns out useful. So, okay, that's, I said, important here. It's tell us this is the only way we can to realize optimization, optimality. So now you write down the solution. Okay, so it looks complicated. What is exactly the means? Okay, so you're doing this calculations is the optimal solution over there. And then I say chemist coming. Okay, so that's the equation called a chemical equation. You solve linear equation, linear system. It might be difficult, high dimensional, depending on what reaction you have here. But this is just a Laplace equation in a sense, okay, complicated, okay, on the level of jumping process. You solve the linear equation, okay, you choose the boundary condition. If the A equal to the 0, B equal to 1, and solve this boundary value problem. Now, computational analysis, okay, you bring still you solve this, do something. You cannot get anything for free. You very carefully compute this commute function, solve larger linear system, and many tools in your hand, we can do it. So once you solve this thing yourself, you just with formula itself, with the often controlled formula itself, you get the solution. It's HAB, I call the solution of HAB, the solution here. So now you would do it does here is just have kind of a double, actually, the one, so you just, you're doing the formula, maybe next page. So you basically have a multiplication rate change from this commute function, the A and B, 1 to A, 1 to B. So as the formula become eventually is change the formula. Optimal solution is very simple by solve larger linear system. You solve this guy itself have here. So now I have to say create the, I guess David Chandler, how do you pronounce it? Okay, chemist from Berkeley. And he was first invented the method. And of course, any good ideas, we actually like good ideas. So mathematician will be jumping, and particularly Y9E, and the many number of people follow up. Okay, this is a beautiful idea to work along these lines, quite a lot along this line. So now we will sort of really completely explain all the behaviors for this. Okay, so that's one. Okay, the computation become how to cover the high dimension. So here's sort of the solution. So you have basically you doing the jumping process. Formula is extremely simple afterwards. So you doing this original jumping rate from this guy to there. So that's our way writing the jumping process. This state to this state is the probability jumping kernel, or called Lavi kernel over here. So now what it does here, you're doing something, you solve this large linear system, you have the y, you jump into y, from this jump to y, I multiply this fact from the linear system. I do the new jumping process, I do Monte Carlo simulation with modified jumping rate by this ratio. And then first of all, this is the optimal one. And this guy do not break down original bridge, and computational friendly if you have to solve a large linear system. And this is a solution computationally we should do. Okay, so that is the idea bring to. Okay, I promise maybe finish up a little bit earlier. Because I don't want to go to any technical detail. Okay, so I guess so. Let me summarize what I try to say. At beginning, look at the classical chemical reaction. It's a monster equation. It although it looks simple about chemical reaction equation, the nonlinear system with polynomial nonlinearity, no structure. Then we slow studying large deviation realize it's actually the Hamiltonian system. So it's Hamiltonian structure bring. And about Hamiltonian system itself, then you write down this reaction equation in terms of Hamiltonian flow plus dispersion. And Hamiltonian flow is heavily rely on free energy or stationary solution to Hamiltonian equation. And how to study this question is a monster, because that is not unique. So that's come out called the VKKM theorem to have selection principle for that. And this everything done by rigorously. And then finally, of course, this understanding on the Hamiltonian structure, we believe, and a particular typical problem, computer transition path, and then we bring to this optimal solution in the sense important sampling, in the sense you compute the optimal change measure. Then you solve very simple, large, simple means sense, solve the large linear system. Then you do very simple Monte Carlo, you change the rate by fact, pre-fact jumping for this fact. Then you get the optimal solution. Actually, we did some numerics for, the 40 atoms. Is not too heavy. Then you do actually is a speed up dramatically. Because anything with Monte Carlo, we all have experienced. Anything important sampling dramatically change efficiency. So this actually is one example we learned from chemists. With this, I thank you very much.